In this video, we will talk about some techniques that do not have an explicit name but are very useful in solving problems on Codeforces, LeetCode, and AdCoder. Let's start with the easiest version of the problem, where you are given an array and you have to partition it into exactly k blocks, k disjoint blocks that cover every element, such that the size of each block should be at least L, but the total number of blocks should be exactly k. And after you have done this partition, let's compute the sum of each block. You sum up all the numbers in this block, call it S1. You call it S2. Call this sum, this yellow sum as S3 and this red sum as S4. Then you sort all these sums in order. So suppose S3 is the smallest value, S1 is the second largest value, you could say, second smallest, then S4 and then S2. So S2 is the largest sum of any block. So your goal is to maximize the sum, maximize the largest sum of any block after doing the splits optimally. So I'll just reiterate the problem. You are given an array and you have to split it, you have to chop it up into several smaller blocks, and each block should be of length at least L, and there can be multiple ways to do this chopping because you don't have to make the length exactly L. So the first block could either be of length L or it could be of length L plus 1 or L plus 2 and so on. But there should be exactly k blocks. So once you have done this division, you have to compute the elements, compute the sum of elements in a single block, call it SI, and then sort all SI and compute the maximum sum of a block. And you have to maximize that maximum sum. You have to partition it in such a way that the block with this sum, suppose this is the maximum sum that you are getting in this configuration, then you have to prove that there is no other configuration where you can still do the partitioning into k blocks with each block with length at least k, such that the resulting sum, the highest block sum, is greater than this mx. So how do you solve this problem? So at first this might look like a complicated, very difficult dynamic programming problem, but I assure you that this is not. In fact, this can be solved simply via contribution technique. But the contribution technique that will be used in this problem is very different from what I have been discussing so far in my videos. So let's start with how anyone that is completely new to this problem, and if they kind of like, if they are convinced that okay, it can be solved via general methods only, no need for fancy dynamic programming algorithm and such. So how do you apply the contribution technique on this version of the problem where you have to split it into exactly k blocks? So you might wonder, okay, if this is your array, then let's consider the optimal split. We don't know what it is right now, but there has to be some optimal split. So suppose this was the optimal split, we don't know yet where these green borders end and where these yellow borders end. So if this was the optimal split, then one of these sums has to be maximum. If this is S1, this is S2, this is S3, and this is S4. So one of these has to be maximum. So assume that without loss of generality that S2 is the maximum value. Then you can notice that the maximum sum of any block will be a subarray of the original array, right? This means that if I can try all possible subarrays and check if they can create a partition, then we should be good. So our strategy for contribution technique is, let me write that down. So this time we want to apply the contribution technique. And how do we want to do that? you you pick any subarray, let's say a I comma I to j, and you ask, is there a configuration in which you can have k blocks and the block and I to j form a single block with maximum sum, right? If you can try out this problem, if you can try out this contribution technique for all the possible subarrays, then you would have definitely gotten your answer. So this S2, we do not know where the block starts and where the block ends. But if we can find out for each subarray, suppose this is the subarray, we ask the question, is there any configuration? So we ask the question, is there any configuration in which this block exists, plus it also has the maximum sum, right? Because we are looking to retain the maximum sum, which is S2. So we are interested in a possible configuration as well as this block has to lead that round, right? Like if there is, suppose there is a configuration in which this block is feasible, like suppose you have this and this, then it is possible that this block has the maximum sum. In that case, you are not counting this contribution correctly, right? Because from your contribution technique, you have defined that you are only looking for the answer where this element acts as the final maxima, because we are only interested in the final maxima. So this is how you would define the definition for the contribution technique. But how do you actually solve this contribution technique problem? Like, is it an easy problem than the original version, or is it still a difficult problem? So let's explore that. We have our array over here. Okay, now you can notice that if you have this big array and you want to apply the contribution technique, basically you want to fix any subarray from I to j. This is the subarray that you want to fix, and you want to ask the question, can you build a configuration in which this element is one block, this subarray is one block, and it also has to be the maximum block. Maximum block sum, right? So how do you even begin to solve this problem? So you can see that if this block is one block in the final array, if this subarray is one block in the final array, then it has split these subarrays on the left hand side and the subarrays on the right hand side. All the elements on the left hand side and all the elements on the right hand side. So there has to be two checks. First of all, there is a feasibility check. That is it even possible to create a subarray, or is it even possible to create a partition in which this block appears as one valid block? So this is the feasibility criteria. Right now, we are not even worried about how will we make this as the maximum sum in that partition. We just ask the very simple question, is it even possible to take this block as a valid partition? So how do you answer that question? So in that case, you can see that you have to make a total of k blocks, right? And if this is one block, then there has to be a total of k minus 1 blocks that are coming from the left hand side and that are coming from the right hand side. So suppose the total number of elements on the left hand side is, let's say, p, and the total number of elements on the right hand side is q. So you should have something like, how many blocks can this p elements create. So your goal is to create exactly k block, right? Exactly k blocks, and one block you have already created. So on the left hand side, you want to construct as much block as possible. So you create the first block, you will create it with length only L. Why not L plus 1? Because you want to maximize the number of blocks that you can create. Now you might wonder, why are we maximizing the number of blocks that we can create? Because if you end up creating extra blocks, like let's say you end up creating k plus 1 blocks or k plus 2 blocks, there is nothing, no harm in it, right? Because this length is greater than or equal to L, this length is greater than equal to L. Just merge these two blocks into a single block, and then you are now back to exactly k blocks. So that is why it is always optimal to retain your chances of creating as many blocks as possible. So you will create, you right now you're just checking for the feasibility, right? Is it even possible? So you will keep on creating blocks of length L on each side. So how many blocks can you realistically create? On the left hand side, you can create these many blocks, p upon L, where p is the count of elements on the left hand side, lower bound basically, low floor. On the right hand side, how many blocks can you realistically create? That is nothing but q upon L. This is the maximum number of blocks that you can create, right? Let's keep in mind that this is the maximum number of blocks possible. Like if you tried your best, even then you cannot exceed these many blocks. So the right hand side can only provide this much blocks to you, no more than that. And the left hand side can only provide this much blocks to you, no more than that. And this center section will provide one block. So if that is the case, then you can see that if this condition holds, that is if the number of blocks on the left hand side plus number of blocks on the right hand side plus 1 is greater than or equal to k, then we know that a partition is definitely feasible in which this entire subarray gets its own block. And why is this greater than or equal to term appearing? Because like I said, if you end up creating, like let's say k plus 100 blocks, right, from this equation, then no worries, all the extra blocks that you created on the left hand side, you can keep on merging them, and then you will, in each step you can reduce the block count by 1, and you will eventually reach k blocks if you want. So there is absolutely no harm in making as much blocks as you want, because you can anyway combine them later. So if this condition is satisfied, then you can say that this subarray is feasible. But now, since we were solving the contribution technique problem, we wanted to find out two things. One is the feasibility, and the second thing is, we said that I want this block to be the maximum sum block so that I can take the contribution of this block in my answer. That is what we wanted, right? That is how contribution technique usually works. You ask, is there a configuration in which this element is the maximum, right? For example, to if I ask you to tell me the maximum sum subarray, okay, and let's not go the DP approach or the divide and conquer approach. If I just ask you this question, solve the maximum sum subarray via contribution technique, how would you do that? You will say that, okay, I don't know what the maximum sum subarray is, but it has to be one of the subarrays. So why don't I try out all the subarrays, and then I take those as possible candidates, and then I take the maximum over all subarrays, right? So this is one prime example of contribution technique, wherein you are saying that you are not aware which subarray is optimal, but if you blindly try each and every possibility, then you will never miss the answer. So can we apply the same technique over here? This time we want to blindly apply the same technique, wherein we say that we do not know which partition gives your optimal answer, but we do know that the optimal partition will be contributed by a subarray only. So that's why we ask this question: can this subarray give me the maximum sum in all of the partitions that it will participate in? So how do you answer this question? So suppose this sum is S star. Suppose you have computed the sum of this subarray. This starts at I and this ends at J. Then you can notice that for the feasibility check that you have already done, you know that yes, there is at least one configuration in which this subarray can be a single block. It will get its own block. But how do you ensure that this S star remains maximum? Because how do you know? In the feasibility check, we just said that you can have blocks of length L, 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 and so on. But some blocks, what if some blocks end up creating a sum that is greater than S star? So how do you even find that out, right? Because you don't necessarily have to end the first block over here. You can as well end the first block over here with length L plus 1. And you can end the first block at even length L plus 10 if you wished, right? Because we said that if the total is exceeding K, then you are allowed to freely merge the block. So this means that there are various possibilities in which this element will get its own block, but in some of these possibilities it will be the maximum sum, in some of them it will not be. So that is why this problem is actually very difficult to answer. Like, this question is very difficult to answer about whether there is a configuration in which this gets its own block but it is also the maximum. And what is the problem? This maximum constraint that we are enforcing two things. This subarray should get its own block from I to J, and then this block should have maximum sum. And finding and making sure that nobody exceeds this sum is getting very challenging, because you don't know where to start and optimally end the subarrays on the right hand side. Plus, what if you are considering this as the maximum and there is actually no way to prevent the sum from becoming bigger than S star? So to solve this problem, this is where the technique comes in. So in the in this trick, what we do is we start with this contribution technique from earlier, okay? And this time we say that we'll not ask this difficult question. And why is this question difficult? It's all becoming difficult because of this maximum sum criteria that we have placed. If you had just asked a simple question, is there a configuration in which you can have k blocks and this element gets its own block? We just saw that that was a very easy question to answer from the feasibility check that we had done earlier. So let's edit this question and let's ask the weaker version of the question instead, not the difficult version, right? So you ask, is there any configuration in which you can have k blocks and this element gets its own block? But how does it actually help us solve the problem? Because the problem was all about maximizing the sum of the block. And if you just check the feasibility, like how is it even possible to apply contribution technique here? So now I'll show you why and exactly how this technique works. So let's start with the array and assume the optimal configuration. Right now we don't know the optimal configuration. Then if it can be split into several smaller blocks like so, let's say, okay, and assume that this is the maximum sum, okay, you don't know yet what it is. Now one thing that you do know that this will be one of the subarrays. Now what if I try to play dumb and I say that okay, if 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 this subarray can get its own block, like if the feasibility constraint is satisfied, like this subarray, we say that a subarray is feasible, we will say that a subarray is feasible if it is possible to partition it into k blocks, if it is possible to partition the remaining into k minus 1 blocks, as we discussed earlier. So if this subarray is feasible, there is no way to guarantee that this is the maximum amongst all of them, right? There is no way to guarantee. But what if I said that if you look at the earlier problem that we discussed about the maximum sum subarray, okay, in the maximum sum subarray, let's go back to the basics. In the maximum sum subarray, I tell you to find maximum sum across all subarray. So in this version of the contribution technique, you still iterate over I to j and you form this block, and then you keep on doing this. Max is equal to you keep on doing mx is equal to max of mx comma sum of I to j, right? This is the version for the contribution technique on the maximum sum of a subarray. So what exactly are you doing here? Now notice a pattern that every time you explore a subarray, you kind of believe that this has to be the maximum, and then you retrospectively like correct your decision by taking this max factor over here. So behind the scenes, what we are doing is we are creating a list of candidates. So we are saying that okay, I don't know whether this subarray that I have just created, I don't know whether this can be the maximum sum subarray or not. But one thing that I know for sure, that is if the sum of this subarray is equal to 10, then the maximum sum subarray has to be greater than or equal to 10. That part you know. So that's why you keep on taking the maximum values seen so far. So this means that if this subarray has sum as 10, so this is a possible candidate for the final maximum. So you maintain a candidates list. Then when you explore other subarrays, so suppose you explored this subarray and this subarray has a sum 20, then this is also one possible candidate for the maximum. So you add it in a list over here. So if you keep on doing this, you will get O of n square candidates because there are these many subarrays, and then you take the maximum out of all possible candidates. This means that to solve the maximum sum across all subarrays problem, you could just pretend that you are one of the possible candidates, and you can keep on adding all of these candidates into a bucket, like this candidate produced a result 20, this candidate produced a result 20, 10, 20, then another candidate might produce 5 and so on, and then you take the maximum from this box. Now why will the maximum from this box be a valid answer? Because here you have collected all the possible candidates, right? And suppose this is the optimal sums, this is the maximum sum subarray. So since you have explored every possible subarray, then at some point of time, this subarray must have also gotten into the candidate set. And since this is the maximum, then this will always lead the maximum set, candidate set. So now you can see that when we iterate over all the subarrays, we don't actually believe that this can be the maximum. We kind of pretend that okay, can this be the a maximum? So we treat it as a candidate for the maximum in the maximum sum subarray problem. So can we apply that same trick over here? This time we say that, okay, I don't want to ask whether this array can be the maximum sum block, right? I just want to ask, can this be a candidate for the maximum sum block? So yes, see, if you have, like, let's say S1 in this split, S2 in this split, S3 in this split, S4 in this split, like all of these are sums of these blocks. So the candidates are S1, S2, S3 and S4. Who will win? Whoever is the maximum out of these, right? But this is just one partition, which is the optimal partition. But if I had some other partition, like say, like if you had this partition where you had P1, P2, P3, P4. Now, is there any harm in considering this P1 as a candidate? There is no harm at all. Why? Because if P1 was indeed greater than the max from this list, then this should have won, right? If this is feasible and P1 is the maximum sum that is achievable, then why did you say that the answer was S3? So this means that even if P1 is smaller than S3, even if you count it as a candidate, there is no harm. In fact, there will be as many candidates as, so how many candidates will there be? So there are k blocks, so k candidates for each configuration. So the total number of candidates is equal to k into number of configurations, right? So if we can explore all the possible candidates and then take the maximum out of those candidates, we would have our answer. So why is this statement true, that if exploring, let me write that down in case it's becoming too vague. So this time we'll follow a different strategy. Explore all candidates, right? Don't try to find the answer. Don't try to find out the answer. Okay. This time we'll just explore all the candidates. Candidates being the keyword. We'll not try to find the answer. And then the maximum element in the candidate list is your answer. Why? Why is this true? So let's see. This time you are saying that give me all the possible candidates and make sure that you do not miss any candidate. So when can this subarray be a candidate? So I'll just remind you that I am considering all possible configurations that can exist with k blocks, and then for each block I am considering them as a candidate from S1, S2, S3 and S4. So these many candidates will be there. So when do you decide that this subarray can be a candidate? If it is a feasible one, right? If it is a feasible candidate. And when can it be a feasible one? Only if the left hand side plus the right hand side plus this one block combined can create at least k blocks. That part we have already discussed. So if this is a valid candidate, and let's suppose its sum is x1, so you maintain a list where you write down x1. Then you explore another subarray. Suppose you explore this subarray. So this subarray can also be a candidate. Why? Because when you are exploring this subarray, all the memories of this subarray has gone, right? Because you are exploring each subarray independently. So then you will ask the question, can this yellow block be a candidate? If the left hand side and the right hand side and this block can create k blocks, then yes, it can be a candidate. If it is a candidate, you write down x2 over here. So this means that you will have a maximum of total of O of n square candidates, because there can be O of n square subarrays. But not all of them will be valid. So valid candidates, basically the feasible candidates, will be less than exactly O of n square. And why is that? Because every time you select a subarray as a candidate, it's not guaranteed that the left side and right side have enough ammunition to give you k blocks. So some of these subarrays will not even act as the candidate. For example, you might be very tempted in taking the entire array as one candidate because it has the maximum sum, assuming all the entries are positive. But in that case, this is not really a feasible candidate because the left hand side and the right hand side cannot produce k elements. So you have to count the feasible candidates and you keep them in a set, right? Now my claim is that the maximum feasible candidate is your answer that you are looking for. Maximum feasible candidate. Now let's see why this is true. Why this statement is true, that once you have collected your feasible candidates, whatever the maximum is from those, they will be your answer. So first of all, let's consider the original split again. And let's say this is the split. So first of all, let's guarantee that we have not missed any of the blocks in the optimal partition in the candidate list. So why have we not missed this block? Because when we were trying out this subarray from I to j, then we would have gotten the feasibility answer as yes, there is a configuration in which this entire subarray can get its own block, because these parts can create 3 blocks. So this candidate will not be missed. It will be present in our feasible candidates list. Then when you are exploring this subarray, then also you would have gotten the answer as yes. So, and then you can repeat the same thing for all the blocks. So one thing you can be sure, that all the partitions from the optimal configuration are definitely present in the candidates list, right? And suppose in the candidate list you might have 5, 10, 20, 30 and 100. So what does this 20 means? It means that there is at least one configuration in the world where some subarray gets its own block with a sum as 20 and other elements combined together to form k minus 1 blocks that is needed. But what does this 100 mean? This means that I know that there is another configuration in the world where one subarray gets its own block with sum as 100 and the other element combined together to create k minus 1 block. So why would I pick the 20 block, right? I would pick the maximum block, maximum feasible candidate. Now the answer cannot be greater than this. Why? Because if the answer was greater than this, then there has to be some configuration. And if there was some configuration where this sum was becoming 200, then when we explored this subarray from I to j, and when we must have definitely given this subarray its own block, then why did it not pass the feasibility check? If it is indeed a valid solution, then it should have passed the feasibility check. So this means that your answer in the candidate list is the final answer. So now the algorithm for the contribution technique, this time you'll realize that we are still iterating over all subarrays. So you do something like this. You iterate over all subarrays, but instead of asking, can this subarray be the maximum block in a partition, in a k partition? This is the difficult question that everyone asks, right? As soon as they see a contribution technique on this problem, you ask a simpler question, and the simpler question is this: does a k partition even exist? Does a k partition even exist where this subarray gets its own block? If yes, then this is a candidate. It might not be a good candidate, because it is possible that you might have selected better candidates before it, but nonetheless it is a candidate. Just like in maximum sum subarray problem, everything is a candidate, right? There are O of n square candidate. So this means that all you have to do is iterate over all the subarrays from I to j, right? Suppose this is j. You ask the feasibility problem, and you know that feasibility check you can do in O of 1. Why? Because you know the number of elements on the left hand side, which is p, number of elements on the right hand side. So feasibility check can be done in O of 1, and you have to compute the sum of this subarray. That can be done via prefix sum, right? that can be done via prefix sum. So the overall time complexity would be O of n square, which is the total number of candidates that you have to explore, right? And this will work whether the array elements are positive or negative, because we have not made any assumptions about the array elements being positive or negative. We have explored everything, literally everything, because you have explored all possible candidates. So now you can see how the solution to this problem is so simple yet so magical, because you wouldn't ever believe that just iterating over all subarrays and then computing their maximum sum would give you the answer to this complex problem where you had k blocks and every block has to be of length L and whatnot, right? And all of these hinges on the feasibility check only, which is just a mathematical check. So can we improve the time complexity any further? So if the array elements are if the array elements can be negative, then of course we cannot. But let's assume for now, for version 2 of this problem, assume that AI is greater than or equal to 0. Then do you really need to explore all the candidates? Because there are O of n square candidates, right? Because if A of I is equal to greater than or equal to 0, so when you are applying the contribution technique centered at this element I, then you will realize that from this I, what are the possible subarrays that are feasible? This could be feasible. This also could be feasible. This also could be feasible. But notice that each time you are shrinking the right side range. So you are making the right hand side more difficult for you, more difficult for it to give you the remaining blocks, right? So it is progressively becoming more difficult to get remaining blocks, right? Remaining blocks are k minus 1. So you keep on increasing. So this means that at some point your feasibility check will fail, right? At this point feasibility check will fail. So if at this point feasibility check is failing, then at this point also feasibility check will fail, because if I gave the right hand side so many elements to construct me the remaining blocks and it couldn't, then even when I take away some element from the right hand side, it will not be able to. So we can stop here. But sure, you can terminate early, but then this could still be O of n, right? You might still have to try out a lot of possibilities. So can we figure out some optimal strategy so that for each index I, we don't have to try out each and every candidate? Are some candidates by definition good than the other candidate, better than the other candidates? So you see that if this is I and let's say this is J. So let's see, right now we are convinced that from I to J, there will be some tipping point J, after which the feasibility check will start failing. And if the feasibility check till J is working, feasibility check till J minus 1 will also definitely work, right? So we have to find out what is the maximum J. So how can you do that? This is also very simple, because you know the elements on the left hand side, which is nothing but P by L that we had discussed, which is the number of blocks that the left hand side has contributed, plus 1, the number of blocks contributed by this middle segment that you are creating, and the remaining block is this k minus this one, right? So you have to construct this remaining block from the right hand side element. So if you end your pointer at J, then how many elements are there on the right hand side? So if you consider zero based indexing, so the last element is n minus 1, and how many elements the right side elements can get, like let's say that is n minus 1 minus J, right? So this is the count of the elements on the right hand side, and we have agreed that the maximum number of blocks that you can create on the right hand side is Q by L, right? So this means that n minus 1 minus J by L, okay, plus this term, plus this term should be less than or equal to k. This means that there is a singular inequality from which you can derive what is the right side border after which your blocks will stop getting created from the right hand side. So just to summarize that again, for each index I, you can find out this border of I, and border of I denotes that if you start your block from here, what is the largest block that you can create that is still feasible. And suppose that largest block ends at J, then how do you figure out this J? By looking at the number of elements on the right hand side and the number of blocks that it can create, number of elements on the left hand side and the number of blocks that it can create. Then suppose you have computed this I and border of I for each index I. Now look at a particular index. For this index I, there can be, this can be one block, 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 and so on. So do we really need to do the feasibility check for all of these blocks? No, because we know that if the largest block is feasible, then the smaller blocks are also feasible. But then do we need to take all of these candidates in our candidate set? No, you can actually ignore all of these candidates. Why is that? Because if you have if you selected this candidate with the sum as S1, then when you expand the block on the right hand side by 1, then the sum will be greater than S1, right? So why do you want to track the candidates who will lose the final round? In the final round, we said that we'll collect all the S1, S2, S3 and S4 in a box, and we'll take out the maximum element and we'll print that as the answer. So if something is going to lose in the last round, why even take it? So this means that for each index I, you can just explore one candidate, and that candidate is the one that starts at I and ends at the border of I. It means that this is the largest block that starts at I but still passes the feasibility check. And this should be the best candidate that can originate from this location. So now you only have a total of O of n candidates, and you know that you can check each candidates in O of 1. So the time complexity of this algorithm becomes O of n. So this was version 2 of the problem. Now let us look at version 3 of this problem. And in this version, you are not asked to split the array into exactly k blocks, but greater than or equal to k blocks. You can create as many blocks as you want as long as you create at least k blocks. And this time you are also not allowed to find the maximum sum. Instead, you have to find the kth smallest sum, right? This means that suppose you have partitioned your array like so. This is the first block, second block, third block, fourth block, and fifth block, and every block has its own sum and so on. So you list down these sums S1, S2, S3, S4, S5 and S6, and you sort them. So you sort it like so: S1, S2, S3, S4, S5 and S6. So if k was equal to 3, this means that you have to maximize the sum of the block at position 3. So no matter how many blocks you create, you will do the sorting every time, and then you will find the rank of the kth block, and you have to maximize the block that is at the kth rank when you read from smallest to largest. Now how do you solve this problem? Now this problem might seem very complicated because this is where the rank creeps in, right? And that is where the original title of the video comes from. So the rank to feasibility trick. But we'll see how this problem is nothing but a very simple transformation of the problem that we have just discussed so far. So even though the problem is asking you to compute the maximum sum that is attainable at the kth position, right? Then let's locate where S3 is in our array. So S3 is located over here. But if S3 is located over here, and keep in mind that these values are useless. Why? Because we are creating this entire thing, but we are only maximizing for the S3. So now the answer, the problem says that you have to split into greater than or equal to k blocks. Then what about the block that is on the right hand side of S3? So can you merge these into a single block? Yes, because if there are k plus, because right now right now there is 3 plus 3 blocks, right? There are a total of 6 blocks. But if you merge it, there will be a total of 5 blocks and the constraints will still be satisfied. But if S3 and S4 gets merged, then S3 is eating a larger element to the right hand side, because S4 will be larger than S3, right? In the sorted order, because all AIs are greater than or equal to 0. So this means that S3 will become even bigger. This means that if you had created just 5 blocks instead of going for a 6 block strategy, then you would have gotten a much better chance for maximizing the element that appears at this location. Similarly, suppose S4 was not on the right hand side of S3. On the right hand side of S3 you had S1. So S3 can even eat a block that is smaller than it. They can merge together to form a bigger block, and once they merge together to form a bigger block, then a gap will be created over here and all the elements will shift, right? So this will become the new, so S4 will become the new kth smallest element, which is of course better, right? So this means that we always merge blocks if we can, right? Even if we always merge blocks if you can. So if you have k plus 1 blocks, our claim is that there is no point in having k plus 1 blocks when you want to maximize just the kth rank. And why is this true? Because if this is the maximum block available over here and you have one extra block, then you can simply merge this maximum block to the block that is on the right hand side and you will get a bigger sum, right? Your goal was to maximize the sum at the kth location, right? So once you remove this plus 1, this will become the biggest sum and that will be the maximum. So this means that even though the problems asks you to maximize the sum at the kth rank and then select at least k blocks, we have now concluded that there is a strategy where you select exactly k blocks. But if you are selecting exactly k blocks, the concept of this kth rank goes away, because now you are just looking for the maximum sum of the entire array. And that problem we have already solved before. So in fact, you can conclude that this problem and this problem, like greater than or equal to k and then maximizing the kth rank, is 100% equal, though both those problems are equal. So this is the version 3. Now let me discuss the final version. So this was the version 3. Let me discuss the final version of the problem. And this is the version that appeared in the Codeforces round. And this was in a recent educational round. And this was the problem that inspired this video. So just to make things clear, I converted this into a array problem with numbers and blocks and sum, so that it's easier to visualize. But the original problem that appeared in the Codeforces round was about this. So it had a string and you had to partition it into several blocks. And again, they had mentioned that you can partition it into greater than or equal to k blocks with block size greater than or equal to L, and you have to maximize the kth sorted string, right? Basically the same version as the version 3 that we had seen, but now on strings instead of numbers. So we have already concluded that this configuration is equal to the configuration where your block size is equal to k and you are looking to maximize the maxima, right? Maximize the maximum sum. So in the string versions, in the string version, there is no concept of sum, right? There is no concept of sum of a string. So there they are doing the comparisons directly. Like once you have split into a block, you say that if this block is S1, so this time S1 is not the sum, but instead this entire string. This time S2 is not the sum, but this entire string of the block. S3 is the entire string of the block. S4 is the entire string. S5 is the entire string. So you say that you can still sort S1, S2, S3, S4, S5 by their lexicographical ordering, right? In their dictionary order. So you have to maximize this lexicographical ordering. But you will realize that this problem is nothing different from the array version that you have discussed. In the array version, S1 represented sum and S1's represented sum, and this time S1 represents a big string. So your strategy is same as before. You just iterate over all the sub arrays, but for each I you will only iterate till the border of I, right? Because you know that till the border of I you want to create you want to create the biggest candidate, right? Because you want to maximize, you wanted to maximize the lexicographical ordering. So you will, for each I you will consider this candidate of I as this I comma border of I. So you consider this candidate. So there will be a total of O of n candidates, and you will add them in a set, and then you will take the maximum out of that set, and that will be your answer. Why is that your answer? Same strategy like we discussed before, that we will not have missed any candidate if we have tried all possible subarrays. And we don't actually need to try all possible subarray. We can try the longest possible candidate from any index. So the only challenge with the string version is that the string version cannot be solved in O of n, because string comparisons, when you want to figure out whether S1 is greater than or S2 or not, to take max, right? Your goal is to take the maximum of S1, S2, S3 and S4 and so on. So you have to do O of n comparison. So that's why the time complexity will jump to O of n square, but that is all right, right? That is not a big deal, that this O of n factor is coming due to the string comparison, right? Not due to a faulty logic or a brute force logic or something. So even if you solve this problem, I will link down this problem in the Codeforces in the YouTube comment section. Even if you solve this problem in O of n square, you are good. You will have extracted the maximum value out of this problem even if you solve it in O of n square, because you know that had this problem been in an array, then you could have easily solved it in O of n. But in case you are interested, this string version can also be solved in O of n log n, because all you want to do is you want to sort a set of strings in O of one time. You want to compute the maximum of a set of strings in O of one time. So that can be done via suffix array. So suffix array is designed exactly for that purpose. It can take a list of strings and it can give you what is the maximum strings in O of n time across all these strings, right? So that is why this problem appeared as problem E in a Codeforces round. But I believe that the reason for appearing as E was only due to the fact that the optimal solution required suffix array, but I am claiming that you don't have to solve it via suffix array. This is hardly a D in an edu round if you solve the same version on the numbers array, right? So yeah, that was the video, that was the technique. Make sure to solve this problem on Codeforces, and let me know if you have any other ideas to solve this problem, because this is kind of a deviation from the standard contribution techniques that you might have seen, right? Like ideally, you whenever you process a subarray, you always look at, can this be the answer, right? But now we are seeing a different perspective, that even in the maximum sum subarray problem, we are not actually asking the question, can this be an answer? We are just saying that, okay, this can be one of the answer. Let me just put it into the candidates list and then repeat for all. And the other technique that we learned is, if you iterate over all the subarrays, then there is no chance that you will miss any possible candidate. So the optimal answer has to be the best possible candidate. So that's all for the video. Thank you.